Okay, so 8.3 is going to focus on common logarithms, and we're going to learn how to solve equations today with logs, and we're going to use those properties of equality that we learned yesterday, and we're going to use them to solve equations. So we already talked about a common log. We know it's a log with base 10. So this is the log that we're going to use to solve equations, and then eventually we're going to apply it to different applications. Okay? So the log button on your calculator is the common log. So on your calculator, when you're doing this, all you have to do is type in the log of 8, and then we're going to round to the nearest 10,000th, which we know means 4 decimal places. Because 10,000 is how many zeros in it? 4, so that's how many decimal places it is. Okay, so if you're ever not sure, you can use that to help you. Like 100 has 2 zeros, so the nearest 100th is 2 decimal places. Okay, so this is probably the simplest thing we'll do all year, and then the back page is probably one of the hardest things we've done all year. So we're gonna get a little bit of everything today.
Does that mean?
Okay.
Wow, she just gave me the worst look to that question.
I don't. Yeah, it's not too bad. Okay, so when you are rounding to a place, if it's 4 decimal places, you always look at the one behind it. So when you are rounding to the nearest 10,000th, you look at the 5th place, and that tells you whether it rounds up or stays the same. Now, we did talk about how you can't take the log of a negative. That's true, but that doesn't mean that your answer can't be negative. Remember, a log is the relationship between the base and an exponent. So when you're figuring this out, we have the log of 0.05 equals negative 1.30, and this would be 10 when you round. Okay, this means 10 to this power is going to equal 0.05. Okay, they're just not nice and pretty like the ones that we've been doing. So now we're going to get more into decimals. Okay? Alright, so the change of base formula is something I've already showed you when we were graphing. So the change of base formula says the log with base b of x. If it says log base b of x, we should be able to write that, right? So you have log base b of x equals, okay, because it says log base b of x is equivalent to the log of b, so that is the common log of b, divided by the log of x. Those should be switched in the words, because it's the log of x divided by the log of b. Yeah, will you switch that for me? Nobody in the last hour corrected me, even though we wrote that down correctly. This is how I remember it. So the base always goes on the bottom. So whatever the base is, that will be on the bottom there. Okay? And then when you put that base on the bottom, you can use the common log as the base, or you can also use the same log. Okay? So the base is either 10 for the common log, or you pick the same base. And I am going to show you today where a situation where that would actually be helpful. Don't go ahead though, because I'm going to change this one, okay? Okay, so if you had log base y of x, okay, if you had log base y of x, another way you could use the change of base formula is you could pick a different base and do log base b of x over log base b of y. So instead of using the common log, you can technically use any log you want to. We just use the common log because it's the easiest thing to do. And that's what you guys will do. But I am going to show you when this is useful. Okay, so we're going to express each logarithm in terms of common logarithms. Then we're going to approximate the value to the nearest 10,000. Okay, and like I said, don't do this. I'm going to change the 9 to an 8 here. Okay, so the first thing we're going to do is use the change of base formula. So if I use my change of base formula, then I can rewrite this as the log of 8 divided by the log of 32. So again, the base goes on the bottom. I say bottom instead of denominator because of that alliteration, hoping that it will stick in your mind. And this is the first thing they asked you to do. Express it in terms of common log. So we got to do that first. Now we can approximate the value to the nearest 10,000. When you do that, be careful because some people forget to put the parentheses in correctly. So you have to do the log of 8, close it, divided by the log of 32. Technically, your calculator would do the bottom without closing it. Okay, so it says to round to the nearest 10,000, but this is an exact value. So if it's an exact value, you can just leave it like that. So do that if it's not exact. And that's why I changed that one, okay? Now I told you I would tell you a situation when this is useful, okay? This is useful if you can rewrite these with the same base. 8 and 32 can both be written with what base? 2, right? So it can't be written with 4, but it can be written with 2. So let's say that some teacher said you couldn't use a calculator and you had to simplify that. Let's figure out how we could do that. So let's rewrite it with log base 2. If I rewrite it with log base 2, 8 would be written as 2 to what power? The third. And 32 would be written as 2 to the fifth. Yesterday, we learned an important rule called the power rule, which is where you take that power and do what with it? Yep, you're going to put it in front and you're going to make it a product. So this would be 3 times log base 2 of 2. And this would be 5 times log base 2 of 2. Yeah, why would it be that, Charlie? Oh, were you guys thinking these are the same? Yeah, these are the same, so you could divide them out. But what else could you do? What's log base 2 of 2? Log base 2 of 2 is 1. Yeah, they would cancel. They would divide out, so you could do it either way. You could think of it as, oh yeah, remember, logs assess the relationship between a base and an exponent. So 2 to what power is 2? It's 1. That's why the log base 2 of 2 is 1. Okay, so yeah, this would be 3/5, which in turn is 0.6. So you can only do that if you can rewrite it with the same base. For the next one, we changed it so that you couldn't rewrite it with the same base. Okay, so again, we're just going to write this with common logs. Whatever the log is going to go on top. Whatever the base is going to go on the bottom. This is the first thing they're asking you to do. Okay, and then I want you to go ahead and approximate that to the nearest 10,000. Okay, so I'll give you a minute to do that. And then you can read through this part here. Okay, and then you're rounding to 4 decimal places. Okay, so when you divided, okay, you should have got 1.58496, and then it keeps going, right? So when you're running to the 10,000th, you have to look at this. If it's a 9, what does this do? Yeah, so if this is a 9, look at this number. What's 1 up from 49? 50. So it's 5850. Do not forget that 0 on there. When you're rounding, if it's not exact, you have to keep that 0. Okay? All right, when you are solving equations, we use what type of operations to solve? Like, how do you know that if you have division, you're going to use multiplication? They are algebraic for something else. Inverse operations. Okay, so the inverse operations that we're really familiar with are addition, subtraction, multiplication, division. See, you guys can use these context clues, right? The inverse of a log function is an exponential function. Okay, so that means we are going to use logs to solve exponential equations. Look at that transition word there. You guys writing any essays, putting some buses in your work?
Nope.
Okay, so the inverse of a log function is an exponential function. So we are going to be using logs today to solve. Now, we already solved exponential equations when we could rewrite both sides with the same base, okay? But that doesn't always happen. Yeah, we could write these two with the same base, but we couldn't do that for 27 and 8. So we're going to have similar problems arise, and the way that we solve those is taking the log of each side. So we have to take the log of each side to solve. And because this is new, I am going to go over it pretty slowly to give you some time to write everything down and process. We're going to put an example here, so don't flip over quite yet. And then one thing that you're going to have to make sure you're doing a nice job at is showing your work, which I know is going to be torture for some of you, but I believe in you. I believe you can write it out. Okay, so we're going to do an example. We're going to start with a simple example. Okay, so we have 8 to the power of x equals 50. 8 to the power of x equals 50. No, it's okay. So when this is the problem that you see in your book, the next step is going to be what you're going to write down first. So you're going to take the log of both sides. So this is the first step I should always see. The log of this side is equal to the log of this side. Okay, so just like you can add the same number to both sides, you can divide both sides by the same number, you can take the log of both sides as long as the base is the same. So you can do the common log of both sides, okay? Now we're going to use our power property. Anytime you have a power, where can you put it using the power property? In front. Okay, so this is going to be rewritten as x times the log of 8 equals the log of 50. Now because x is attached to this with multiplication, we can do what to both sides? Divide. Now what are you dividing by? Log of 8, okay? You can never divide the log of 8 by a log to get rid of the log, okay? Logs have to be of something. So you can divide by the log of 8, you can't just divide by a log of nothing. So those will cancel out, and then there are 2 ways that you can write your answer. All right, so if you had something like this on a no calculator section, this is how you would write your answer. And then if you were in a calculator section, it would tell you to round to the nearest 10,000. And then look, if you guys want to, I'll show you some tricks on your calculator. If you use that, you can just go in and you can just make this 50. You would have to insert because it's longer there. And then you'd have to delete that. But log of 50 divided by the log of 8. Yep, and then so 1.881, and then the 2 is going to be bumped up. Okay, so if you have a question that asks you for an exact answer, okay, this is what you would write. This is an exact value. This value is rounded. We're going to do a lot of the rounded values today. Okay, but I want you to understand that this would be an exact value. And when you round, you're not going to round until the very end, until the very last step. Yeah. Okay, so when you are solving the equations and they ask you to round to the nearest 10,000, okay, we know that's 4 places now, and make sure that you don't round until the last step. So 4 places, and then do not round until the last step. So don't round early. You're doing sig figs? Oh, good. Yeah, because you would be off for a little bit. Yeah, if we can be as exact as we can, that's always a good thing. Hey, and then when you have 4 to the x minus 1 equals 5, we're going to start here. Okay, and then the way I'm going to show you to do this is something that can be applied to all of the types of equations that we're doing today. There are a couple of different ways where you can solve these. But because these are a little more difficult, I am going to be writing down how to do it in the margin here. And I didn't give myself enough space for A, so we are going to do these. I'm just going to move them around and not let their positions limit me. Okay? So your first step, okay, if you cannot rewrite these with the same base, which you can't, 4 you could rewrite with 2, but you can't do that with 5, this is when you are going to take the log of both sides. So this is what you would see in your textbook. This is the first thing I want you to write down on your paper. Like I said, it's going to be difficult for some of you to do step by step. So just try to slow down and make sure you understand how the process is working. Now, once you take the log of both sides, that's when you can use your power rule. So the power rule tells you this exponent goes in front. But this exponent is a binomial, so when you rewrite it, you have to rewrite it in parentheses. If you didn't, it would not mean the same thing. It would mean x minus log 4, okay, which is not the same thing that we're going to do. Because whenever you have parentheses, is there something that you usually think of doing? Yeah, great. That's our next step. Okay, so now we're going to distribute. So when you distribute, we're going to write this out as x times the log of 4 minus, and then 1 times anything is itself, so it's just going to be minus the log of 4 equals the log of 5. Okay, now what we're going to do is get all of the variables on one side alone. So if there's not a variable with it, we're going to move it. So isolate variable on one side. So this one you only have one variable. What is our variable? X. So that's exactly what we're going to do. So we're going to add log 4 to both sides. So what that does is it leaves x times the log of 4 alone. And then here you actually have a couple options. So you can leave it like this, that's perfectly fine. Or if you want to condense it, remember that we have the product rule. If you're adding, what could I make this? Log of what? Log of 20. 5 times 4 is 20, right? So it would be less to put in your calculator. And then you could just divide both sides. And I'm going to divide both sides by log of 4. Okay, so, and I'm going to show you that those are going to end up being the same thing. Okay, so you can do the log of 20, and make sure that you don't condense this, because you can't condense this. You could make it division if there was minus. Okay, but when you have the two logs, you can't condense that any further. So just be careful with that. So if you have the log of 20 divided by the log of 4, this is going to be your final answer. So you have 2.16096. So think about how you're going to round that. If you are somebody who second guesses themselves when they round, there's nothing wrong with writing this out and looking at it. Right? And saying to yourself, okay, if I'm rounding here, this is going to tell me instead of 0.9, it's going to be pushed up to what? Yeah, so x is so you can do approximate or equals. I'm not really picky on that. So it's approximately 2.1610. Yeah. Yes. If this was the log of 20 divided by 4 instead of the log of 20 divided by the log of 4, then you could write it out. So I didn't. I said if you had the log of 20 divided by 4 instead of the log of 20 divided by the log of 4, those are not the same. Yeah. Okay, so I know it did sound very similar. So the other way that you could do this, like I said, you don't have to condense it to 20. If you want to do the log of 5 minus or plus the log of 4, I usually do that first, and then divide that by the log of 4, you should get the same exact thing. See how you get 2.16096 just like you have there? That is fine, so you don't have to condense that. Were any of you thinking of a different way to do this part up here? Because this you could do, yeah.
Divide both sides by log 4.
Yep, so at this step, if you divide both sides by the log of 4, this is only going to work if you only have one variable. You're going to see in the next one, we are going to have two variables, and that's why I didn't show it to you like this, okay? So if you divided that, then you'd have x minus 1, yep, and then you would add 1, okay? That is fine if you have one variable, okay?
So that's okay to do on a homework.
If you have what?
One variable.
If you have one variable. But if I ask you for an exact value, you'd have to tell me this. Log of 20 divided by log of 4. Okay? Or log of 5 plus log of 4 divided by log of 4. Now, for B, you're going to see on both sides, in both exponents, we are going to have a variable. Okay? So, if you have variables on both sides, 7 to the power of 2n equals 52 to the power of 4n plus 3. Okay. Our step list is going to be almost identical. There's just one other different thing we're going to do. So first step is always to take the log. Okay, so take log. When you're writing the log, you need to write it in front. That's why, Brennan, did he leave his stuff? You leave your stuff. Take all your stuff with you. Yeah, just in case. Sorry. Okay, and then once you take the log, then you're going to rewrite it with your power property. So take the log, use your power property. Okay, so the power property allows you to rewrite it as 2n times the log of 7 equals, and then do you guys want to try the other side? Okay, so anytime it's a binomial, that has to be in parentheses. Anytime it's a binomial, it has to be in parentheses, or it won't mean the same thing. Then you would just have 3 times the log of 52, and we are going to have to distribute. Okay, so you only have to distribute when there's a binomial. So we're going to keep this 2n times the log of 7. It's going to be equal to 4n times the log of 52. And more. Yes, plus 3 times the log of 52. Okay, so you're multiplying the log of 52 by 4n and 3, and this is what it looks like. Now, this is a little different from the first one that we did because after we distributed, we were able to isolate the variable on one side pretty quickly, but we have 2 variables now. So what we're going to do is we're going to get the variables on one side. Okay, so that means I'm going to minus the 4n times the log of 52. And you can see I'm putting the times there. That's more for me to remember that there's the times. It's not necessary for you to write that in there. Okay, so now on this side, we're going to write this out, and then in the next one I'll show you a shortcut, okay? And write what you have on that side. Sorry. Need my Zycam. No, I think it's that teacher life, you know.
Right. Yeah, nobody else.
Okay, so once you have everything on one side, okay, because you have two variables, what you're going to do is you are going to factor out the variable. When you factor out a GCF, okay, when you factor out the variable, it's the same thing as factoring out a GCF, which is the same thing as the distributed property in reverse. So if you have two variables, this is what you have to do. Factor out the variable. Because what variable is in both of these? The n. And notice I didn't say that we factored out the GCF because we're not going to factor out the 2. We don't need to do that. Okay? But if I factor out an n, if I divide n, then I have 2 times the log of 7. Oh, don't put your parentheses there. And then minus more teacher problem. I thought whiteout was so cool when I was a kid. I remember like my 5th grade teacher had a treasure chest. Do you guys remember teachers having like prizes you could pick out? Oh my gosh, if there was whiteout in there, I wanted that. No, I'm the only weirdo in here. Oh. Well, I did want to be a teacher, so.
I remember this. I was first grade, bro.
Oh, and then you could spend them at the store?
Yeah. It was $5 an hour.
Being a kid is so cool. Let's never grow up, okay?
There's a teacher on TikTok who like pays her students and she charges them rent.
Oh, to like be there. That's what I should do.
It's like $5.
I think everyone's going to be ridiculous. Everyone's going to be gone.
No. It's like the money she gives them, so like pays them.
Well, it's like Monopoly money, right?
Yeah.
Yeah.
I don't know, maybe for much. But it was that round.
Okay, so then when you factor out the n, like I said, it's like the reverse of the distributed property. So if you did n times 2 log of 7, this is what you'd have. N times 4 log of 52, that's what you'd have. All we're doing is factoring out the variable so that we have one variable. And now, to solve, what can I do to both sides? Remember, this is n times this value, right? Okay, so I am going to let you, when it's right next to it, I'm going to let you do this because I know that that's kind of long, okay? But I do want you to either write it out here, so 2 log of 7 minus 4 log of 52, and that way I can see what you're putting into your calculator. Okay, this is the exact value. If it's right underneath it, that's fine, but on this side I want it. Okay?
We don't have to write out twice.
Yeah. Okay, so when you do this, you are going to have to make sure you put that bottom number in parentheses and that you close that one. Those are the places where students make small mistakes and then they do everything right up to the final answer. So before the 2, we just have to insert the parentheses, okay? So 2 log of 7. Yeah, your calculator will think that you want to divide that and it will follow that order of operations. So we have to put the parentheses on that tells us it's a fraction, okay? And then you should get negative 0.9950. Oh, and then, sorry, the sixth step is to divide. Almost. All right, so then I'm going to have you guys try to start C.
All of that.
Just always start with putting the log up to the side.
Yes. Yeah, that's what you do. You always start with putting the log on both sides. Sometimes, like if you start by writing the problem out on your paper, I would leave a little bit of space there so you can write the log without scrunching it in, okay? But like I said, when you're doing this from your book, this is what you're going to see in your book, and then I want your first step to be writing the log. Okay, so were we able to get here okay? All right, now we can distribute. Oh, and then I told you I'd show you a little shortcut. So this would be 5 log of 13 minus p times the log of 13. So again, you're getting all the variables on one side. So if you are adding this over, looks like clog, doesn't it? The clog of 13. Okay, so this is the shortcut. Instead of writing out like that whole line, the reason you're moving this over is so that the variables are together so that you can do what with it? You can factor it out. So if you want to just write P and then write what you're going to have in your parentheses here, that's fine. Okay, so you have p times the log of 6. So if you take out a p, it's just the log of 6. Plus the log of 13. And then your final step is going to be to do what to both sides? Divide. So when you divide, I'm also okay if you just write out your last step like this. 5 times the log of 13 divided by the log of 6 plus the log of 13. Now again, when you have a log plus another log, you can write that as the multiplication of 13 times 6. That would be fine. You would get the same answer. Or you can just leave it like that. And you can calculate. Just make sure that you have the parentheses. I'll give you a minute to calculate to make sure you can do that part all right. Okay, so what did you guys get for P? Yep, 2.9437. Okay, so if your decimal is not the same, then let's check to make sure we did the parentheses. So like I told you, there are a couple of spots where people are prone to forgetting parentheses. The first one is here. You have to put that other parenthesis on. The second one is you need it on the bottom. And you have to close this one and then plus the log of 13. Okay. All right. So we're going to do one application problem today, and then early next week we'll be doing more of this. So it says initially there are 2,000 bacteria in a culture, and the number of bacteria triples each hour. The first thing we're going to do is we're going to write an exponential growth function to represent the situation. Okay, so if they ask you to write the growth function, we're going to use the model that we used in our earlier chapter, where y equals a times b to the x. You can also make the x into a t if it's the time, which is what we'll do. Do you guys remember what the a is? Yep, your initial value. Now, we stated how b is the base, and that's true, but remember when we were doing the tables? And from the tables, if it was exponential, you had to make your own model. What was the base in that case? So it's like, remember what you found? It was called starts with an R. The ratio. Yeah, so what you did is you found the common ratio by dividing the terms so you could figure out what it was going up by. So whatever your common ratio is, that is your base. Okay, so if it's tripling each hour, what would you suspect our base would be? Yup. Okay, so if it triples, your base is 3. If it doubles, your base is 2. If it quadruples, it cuts it in half, 1/2. Okay, so what we're going to do is we're going to write this as y equals 2,000 times 3. And like I said, we're going to use t because t is what? In what? Yep, your t is the time in hours. So whenever you have the time, one thing we want to do is specify the unit, because there are different measures of time, and we're going to be working with problems where sometimes it's days, sometimes it's years, sometimes it's minutes. Okay, so we want to make sure that we have that identified. So this is where t is the time in hours. Okay, and then for step B it says find how long, so that means we're going to find t, how long it will take the culture to increase to 100,000 bacteria, and we're going to have to use logs to solve. Okay, so if this is the initial value, this is the final value of the bacteria. So if we want to know how long it takes to get to 100,000, we have to set our equation equal to 100,000. Okay, and we're going to learn how to solve this with logs. So if you have a value that's multiplied to your exponential function, what you have to do is move this over. So we're going to move it over using division. So we're going to divide both sides by 2,000 so that we have the exponential part by itself. So we have 3 to the t alone here. And when you're dividing, if you have zeros, you know you can just divide those out, right? So 100 divided by 2 is 50. Now we have a problem that looks exactly like the ones above. That's just a little simpler than the ones above. So what are we going to do to both sides? Yep, so you can take the log, you can squeeze the log in there so it doesn't look too messy, you can do that. Okay, and then after you take the log, yeah, use your power property. So the power is going to be t, and you multiply that by the log of 3. Okay, you always are going to use a log to bring down the exponent, and then it's no longer in the exponent. And then your last step is going to be, yep, so like I said, I'm okay if you put that there as long as you write log of 3 on this side. Alright, and then sometimes this will ask you what to round to, sometimes it doesn't. If it doesn't tell you what to round to, I'll be pretty lenient on that. On your test, I'll tell you what to round to. So let's round this to the nearest hundredth. Okay, so if I round that to the nearest hundredth, what am I going to have? 3.56. And then you need to just include your unit, so this is hours. Okay, so it's going to take 3.56 hours for it to increase from 2,000 to 100,000. And that's why we always wash our hands.